All right, let's get started. Okay, so yeah, let's review what we talked about in the last lecture. So in the last lecture, we start from talking about the shifting property of the Fourier transform, right? So basically, if we shift, if I have a shift in the time domain, then in the frequency domain, we're going to have a phase shift, right? And so the reason that is very important is that we can actually use this kind of important property to analyze the received signal and the system property of a LTI system, right? So before, we have two cases that we have discussed. The one case is the distortionless case transmission, and the other case is the transmission with nonlinear distortion, right? So, and for this case, so first we analyze, so what is the output signal look like, right, as a function of the input and the unit response of the channel. And from here, we can see that. So basically, the output equals to the magnitude multiplied the phase part, right? So here is the magnitude, and here is basically the phase, right? So we can write it out explicitly. So basically, here is the magnitude, right? So that's equals to the magnitude of the input signal multiply the magnitude of the channel, right, in the frequency domain, of course. And for the phase part, so we just write down this, but this up to plus minus k pi, right? We need to make sure that, so the value of it is between minus pi and pi. Okay, and here is the definition of the distortionless transmission. So basically, if x is our input signal, so we just multiply that with a constant and then have a delay, right? And for this kind of very special type of system, and we can analyze what the channel looks like, right? So basically, so if we analyze this signal in the frequency domain, so this is what we get, right? The channel is nothing but a constant multiplier phase component, right? And the value of the phase determined by the delay, right? So which kind of makes sense. And here we use the property of the time shifting property, right? So if it's a time shift in the time domain, then it'll be a phase shift in the frequency domain, right? So that's pretty straightforward. And here is the magnitude of the channel. So in this case, the magnitude of the channel is just a constant, right? It doesn't change. And for the phase, again, so it's this part, but we need to make sure that this is within this range, right? We may need to add or minus pi, depends on the value of TD, right? So just be careful on that. Okay, and here are some comments for the distortionless transmission, right? So we say that the human ear is less sensitive to the phase distortion and more sensitive to the amplitude distortion, right? And for human eyes, so it's the opposite. It's more sensitive to the phase distortion than to the amplitude distortion, right? So I think those are just facts, right? So you can take a look if you're interested. All right, and here's the part of the nonlinear distortion, right? In particular, we consider a case where a system is like this, right? We take the input and then we raise it to the power of k, right? And for this kind of very special system, obviously that system is nonlinear, right? So in order to verify whether a system is nonlinear or not, you just need to use the definition to verify it, right? It's very clear that the system is nonlinear, and from the time domain, right? If the input is the g of t, right? If we raise it by k, so in the time domain, it's very hard to see the property of the signal, right? So it's just a signal raised over k, right? What's the big deal, right? Okay, but if we analyze the signal in the frequency domain, so we can see something very interesting, right? The way we're going to do that is, again, using the property of the Fourier transform, right? So here, if we raise g by a power of k, so basically we have a bunch of g multiplied together, right? And then in the time domain, it's a multiplication. So in the frequency domain, it'll be a convolution, okay? So there will be like k, g, f convolutes together. So here should be a convolution sign. All right, and if we do the convolution, so we can basically see that, so the width of the signal in the frequency domain would be k times of a single one, right? So this is exactly the analogy to that happened in the time domain, right? If we do convolution, the signal becomes wider, right? Same here, right? In the frequency domain, the signal becomes wider. In the frequency, it means that we need to consume more frequency, okay? So they occupy more frequency components, which is not desired, right? It's very bad, right? So that is basically what is happening. And so this phenomenon is called spectral regrowth, right? Because we have a signal after some operation, after passing through a system, so we have new frequency component, right? And that is undesired in general. Okay, yeah, and yeah, that is this part. So any questions so far? All right, and after that, we talk about compute the energy or power in the frequency domain, right? Yeah, so yeah, we only cover the first part here, right? So we need to cover the second last part in today's lecture. So basically, yeah, so I didn't talk about this in particular in class, but this is a general case, right? So if I can decompose it, a signal like this guy, right? And then if you compute the energy, and then it's equals to this guy, right? So FT can be any orthogonal basis, right? So for our interest, we are interested in the Fourier or the complex exponential basis, but in practice, right, it's just a mathematical fact, right? As long as the bases are orthogonal and the norm is unit, it's called orthonormal, and then so this equation will be hold, right? So yeah, but in particular, in our case, so what we care about is the periodic signal with its Fourier series, right, and or Fourier transform. Okay, so basically this is the fact, right? So if we compute the power in this case, because we consider x of t as a periodic signal, right? For periodic signal, we can only compute the power, not the energy, right? Because energy is infinity, right? If you compute the power of a signal in the time domain, then what happens in the frequency domain is that it equals to summation of the norm square of all the Fourier coefficients, right? So if you think about this again, so in the frequency domain, it's actually the energy, right? But the physical meaning is still power, because you're right. So this guy is with the physical meaning, okay? And in practice, so what we can comfortably use is that whatever exists in the time domain will equals to whatever exists in the frequency domain. By existence, I mean it's not zero and it's not infinity. Okay? Basically means that, okay, so if we compute the energy in the time domain, and then in the frequency domain, so that's the periodic signal, so we'll compute the power in the frequency, and they'll be equal, right? So whatever exists in this side will be equal to whatever exists on the other side, okay? So that's the beauty of this nice fact, right? And so this is a generalization of it. So basically, we can show that actually Fourier transform is called inner product preserving, right? So if we compute the inner product in the time domain of any two signals, and then it will be equal to the inner product of its Fourier transform. Okay, so it's very easy to show. You can show that using these steps, right? So this general theorem together with what we talked before is called Passarell's theorem. Okay, so basically we can compute the energy in the frequency domain or the power in the frequency domain. So that is very nice. Okay, yeah, and that is what we covered in the last lecture. Any questions? Okay, great. So yeah, let's start today's lecture. Today is our lecture number 10. Okay, and today we have two topics. The first is the energy spectral density. And the second topic is power spectral density. right? And now see how far we can go. Okay, so let's first talk about the energy spectral density. So yeah, let's introduce the concept of the energy spectrum density, right? So in order to do that, so now we consider a system called bandpass system. Okay. So we consider a bandpass system. Or we call that bandpass filter. So basically, it means that in the frequency domain, we have something like this. Let's say here is our system unit impulse response, right? And then consider a system like that. So here is some square, and here is another square. It's metric. And so let's assume that the magnitude here is 1, and here is FL and FH. L means low, H means high, lower frequency and higher frequency. And here we have a minus FL and a minus FH, right? Right, why it's called the bandpass system? So basically it means that if we pass through a signal with this kind of system, right, it's like we use a signal in the Fourier domain, in the frequency domain, multiply that. Right? So only this part are left, and everything else will be 0. Right? That's called its bandpass. Right? And what you have seen in your lecture, in your lab 1, is that you use this kind of filter. Right? It's called what? The baseband filter. Right? So, or low-pass filter. Right? Yeah, of course, what you use there is not exactly this shape. Right? So it may have some weird shape. By the way, anybody check about what you're using in your lab 1? For the low-pass filter? Do you check the exact shape of that in the frequency domain? No? Yeah, if you're interested, you can check, right? So by the way, so basically, if you remember in your lab 1, so I think in part 2 or part 3, probably part 2, I guess. So you didn't do the integral, right? So what you do is that you use the signal, multiply together, passing that through a low-pass filter to get Fourier coefficients. Is that right? Right? So why we do that? Why it works? Right, you can, yeah.
Well, I was going to say in that specific case, it was for rectified cosine, which so it's kind of, it has a maximum amplitude, and then you would filter out all the high frequency components. So all the dips would be gone, and then you're just left with constant.
Very good. Intuitively, yeah, that's the reason. I totally agree. Yeah, but mathematically, we can also have some reasoning. Right? Think about it. Right? So it's not required, but so normally, so we can we can use the idea of Fourier transform to kind of explain that. Right? So basically, when you do an integral in the time domain, so can you rewrite the integral as something else? Right? So basically, you can rewrite the integral as your function convolutes with the unit step function ut. Okay, signal, right? If you want to integrate over gt, use gt convolutes ut, right? So that's basically your integral. Okay, and then since this is happening in the time domain, so in the frequency is gf multiply your what uf, right? And what uf look like? Okay, it's more or less like a low-pass filter. Okay, so that's why it works. Does that make sense? And you can see the coefficient doesn't match, right? And yeah, that's probably the reason. Yeah. So does it make sense? Somehow? Yeah, you can think of this problem deeper and see whether you really understand it, right? So yeah, you can use what we have learned so far in the analysis in the frequency domain to explain that, right? So yeah, just some comment on the lab 1. Anyway, so yeah, this is in lab 1 use a low-pass filter, but now we're gonna use something else. It's a bandpass filter. Okay, and mathematically we can write this as a function, right? So h of f equal to this guy, so it's equals to 1 when fl less than absolute value of f less than fh, and 0 everything else, right? Otherwise, Okay, so this is what we have, and we'll assume a system like this. So now we consider everything in the frequency domain. Let's assume that our input signal is g of t, and in the frequency is g of f, and we'll assume this g of t is real, right? For simplicity, because if signal is real, then we have lots of, symmetry property that we can use, right? So which can make our life a lot easier. And we pass this signal through a system. And then we have output signal that is y of f, and clearly y of f equals to h of f multiplied g of f, right? Yeah, just introduce you a system, right? So what we have been talking so far has nothing to do with the energy spectrum density yet, right? So we're gonna see that later. Okay, so now let's introduce, the energy part, right? In order to compute the energy of yf, right, what should we do? Right? Yeah, so basically the energy of yf or yt, right? We assume that, g of t is real and aperiodic for simplicity. Okay? So we could compute its energy in the frequency domain, right? So what's the energy of what is the energy of this guy in the frequency domain? The energy let's say Ey equals to what? Yeah, we just say that, right? Yeah, let's assume that signal is aperiodic in the time and aperiodic in the frequency. Okay? And then how can we compute the energy in the frequency? Any idea? Yeah, just the norm, right? Norm of yf, or in other words, so it's an integral of yf df, right? So this is the definition of the energy. Is that right? So why we can do that? Because of the Parseval's relationship, right? So basically what we do is that we compute the energy in time, so which is gt, oh not gt, yt squared dt, right? So this is a definition of the energy of the signal, right? This is equal to that, right? Why is it equal to that? Because of the Parseval theorem, right? We compute whatever in time or equal to whatever exists in frequency, right? Does that make sense? So everybody are with me? Are we good? Yeah, this is very important, right? We need to, we need to understand why we can do this, right? Is that clear? Questions? Yeah.
How do the units work out for that?
Unit. Yeah, units. For example, a unit can be, if it's the energy, it will be in joules. Yeah. And then the unit of this is all joules. Yeah, the unit will not change.
No, but I just like, how do you convert from something? Like, how are we converting it to joules? I guess.
Convert it in joules. What do you mean?
I don't know. I guess my question is kind of weird.
Yeah, I don't think it's weird. It's a good question, right? Normally, okay. So yeah, what I'm going to say is that this could be an abstraction of energy, right? In practice, how do you compute the energy? I think if my physics works, so it should be like maybe the volts, right? Square divided by r, and then you do a integral of it over t. So that will be our energy, right? Is that correct? Or the current square multiply r, and then you integral that, right? Right. You can see that whatever if you use voltage here or if you use current here, it's always a square relationship, and that's what we're doing here, right? So this square, and if you either divide it by constant or you multiply it by a constant, that will be your energy, right? But it's a constant, we don't care. Then we define that as energy. Does that make sense? Yeah. So that's normally what we do, right? Because constant doesn't matter much normally. That makes sense, right? And therefore, you can say we don't have a unit here, right? Because it's an abstract. But if you really want, you can use whatever energy, the unit you want. Yeah, very good. Any other questions? And why this equal to that is through mathematical. It's a mathematical relationship. Yeah. So we just prove it in the last lecture, right? Yeah, that good? Okay, great. And with that said, so right, we can do one more step. So basically, that equals to nothing, but we just plug YF in here, right? YF equal to this, right? So that is H of F times G of F dF square, okay? And now, what is interesting is that, so because H is that, right? Only this part and this part left, everything else will be gone, right? So we can break this integral over two parts, right? So one part is the negative part, and the other is the positive frequency part, right? Basically, it means that we integral from minus FH to minus FL, and then the magnitude of H is 1, right? Or the value of H is 1. Then only GF square dF left, and on the other side, so it's FL to FH, and also this part left, right? Yeah.
Would you be able to combine that if they're like perfectly symmetric?
Very good. Yeah, we can. Yeah. Yeah, we can directly combine these two for sure. Yeah, very good.
Just like a coefficient of like 2 times.
Exactly. Yeah, so that we can, yeah, very nice comment. We can basically write that as this. Right, why we can do that is because we assume G of T is real. Right, in real, we have this very nice relationship, GF minus equals to G conjugate of F. Right, and then, so their absolute value would be identical. Okay, very nice. Yeah, and actually that is what I'm going to write next. Very good. Okay, great. So now let's see what is kind of interesting. Okay, so we didn't specify the value of FL and FH, right? So FL and FH can be some whatever number. Right, so it basically means that whatever bandpass frequency that we're going to using, then the output energy is something like this, which is not changing, and then do the integral over FL to FH, right? And so therefore, so this item can be understood as kind of density, right? Because when we compute the energy, right, this doesn't change. I mean, the format doesn't change, right? Of course, it's a function of F, right? And then we just need to change this part to get the energy of the output signal, okay? So this is some form of energy, right? Oh, sorry, some form of density, right? So therefore, we call that as the energy spectral density, because in the frequency, that's why we call spectral, okay? So that's how, how we get this concept, right? So now let's write down the definition here, very important. Energy spectral density. Or we call that ESD for short. Okay, so definition of that is, we say the ESD of a signal G of T. So that is nothing but, so we have a notation of psi G F. So that is G F square. Okay, so if we do the integral of this guy over F, then we're going to get the signal energy for the specific frequency band. Psi. Psi. Look like phi, but yeah. Yeah, I think it's written like that, right? So phi is like there's a circle, I guess. Yeah, psi. Okay, great. Okay, let's see a very straightforward example of it, right? So we have seen, let's see a very straightforward example. We have seen this kind of thing before. So what if g of t is a rectangle signal, t over tau, right? So this basically looks like this. We have 1 here, we have tau over 2 here, minus tau over 2 here, and then t, right? So we're going to see the energy spectrum density of this. We call that rectangle pulse. Of a rectangle pulse. Okay, so this is basically a signal in the time domain, and who can tell me what is the signal in the frequency domain? So I've seen this so many times. Yeah, who still remembered? Come on. Yeah, very good. And do you remember the details? Like tau, think, pi, tau, f, right? I think it's pretty easy to remember. Just remember it, think. Okay, so we have a tau here in front and we have tau here inside. Everything else is pretty standard, right? Remember that, right? So we're gonna use it so many times in this class, right? That's the most important signal I think we use it in communication, because this is normally what we transmit in the time domain. Okay, square root form, easy to transmit. Okay, great. Okay, and then we know that, and then basically the ESD is nothing but this guy, right? So the psi g of f is nothing but square of this guy is tau square think square pi tau f, right? So that's basically what it is, right? You can draw that, right? So basically, the shape of this is pretty much look like that. We just need to make it, square, no negative part. Okay, so that's a very straightforward example. So now let's see a more interesting example. So I think probably starting from the next lecture, we're going to talk about modulation, right? So which is a very important part in communication, in any communication system, right? And we mentioned a few times. So modulation is nothing but we move the signal from one frequency position to another frequency position, right? So in the time domain, it's like multiply the signal by a cosine waveform or by a complex exponential waveform, right? So now let's see the symmetric case. So let's say the ESD of a modulated signal. Okay. So we assume the signal S of t, so that's a modulated signal. That equals to g of t multiply a cosine 2 pi f naught t, right? So this is what we do. Okay, then let's see what is the ESD of this guy, right? So we know the ESD of g, right? So basically, psi g of t, that equals to g f squared, right? So this is what we know here. Okay, so let's see how we compute that for S of t. Okay, so for simplicity, let's assume g of t look like this, or let's say psi of t look like this in the frequency domain, right? We have I say b here minus b here for simplicity. Okay. Yeah, maybe I would say that's g of f. Yeah, that may be better for the later use. Okay, but psi of f is just square of it, right? The shape will not change. Yeah, let's see how we could compute it. So first of all, in the time domain, we multiply cosine, right? So can you tell me what is S of f? What happened in the frequency domain, right? Can you write down S of f in terms of g? Right, we can write that as what? g of t multiply, use complex exponential to represent this guy, right? J 2 pi f naught t plus e minus 2 pi f naught t, right? So we can. Then g is multiply one complex exponential and then multiply another complex exponential, right? So if it's a phase shift in the time domain, then in the frequency that is what? Yeah, say it if you know. Very good, right? So therefore, we have a half g. So here is a plus, then in the frequency we have a minus, right? And for the other one, it's the opposite, right? G f plus f naught. Okay, so this is the Fourier transform of SF, right? That clear? Okay, and then with that, so now we could compute this guy, right? So let's compute it over here. All right, so basically now psi s of f, so that will equals to nothing but the SF squared, right? SF absolute value squared, right? So that equals to, so that squared is 1 over 4. And then we have g f minus f naught add g f plus f naught squared. Right, let's compute it. So basically, this is, we can write that as what? By definition. So it's this signal, right, multiply whatever, this conjugate, right? Right, so this is the definition of this norm square. So basically, yeah, that equals to, so we definitely have this multiply that and this multiply that, right? We can write that first. So we have nothing but g f minus f naught square plus 1 over 4 g f plus f naught square, okay? So these two terms will be left, and then we'll have two cross terms, right? So the cross term would be this guy multiplying this guy, right? So g f minus f multiply g f plus f naught conjugate. And then we'll have one more term. So that is this guy multiply that guy, right? So g f minus minus f naught conjugate times g f plus f naught, right? So this multiply that. And then we have all of this, okay? And you can see, so what is the relationship between this and that? Right, so this is the conjugate of this guy, right? So this is the conjugate of this guy. So basically, we can combine these two as, so if some number add its conjugate, it basically we take the real part twice, right? So basically, that equals to 2 times the real part of g f minus f naught times g f plus f naught conjugate. I take the real part of it, right? Yeah, any questions so far? That clear? That clear? Yeah.
Can you explain why you went from squaring the entire term to multiplying it with its conjugate at the top?
Oh, you mean how we get from here to here?
Yeah.
The definition, right? So this guy defined as x times x conjugate.
Oh, okay.
Yeah, it's a complex number, right? If it's real, then just x times itself, but it's conjugate, so it's defined like that, right? In other words, if you like, let's assume x equals to a plus j times b, right? So then this guy equals to what? A squared plus B squared, right? And then, if plug that in, it's A plus J times B, A minus J times B. So minus is the conjugate of this guy, right? And that equals to that, right? So that's the definition. That clear? Okay, great. Okay, so now let's see. So this part is ugly, right? So what does that equal to? Right now, let's think about this. So basically, this is GF. And now let's draw the modulated signal, right? If we do the modulation here, so here would be what? GF plus F naught, and here is minus F naught. And here would be GF minus F naught, right? And here is F naught, right? So this is the modulated signal XF, okay? Right? So now can you tell me what that term equals to? Yeah, it's like this guy multiply this guy. But remember, this guy's here, and this guy's over here, right? Then what's that equal to? Yes?
Would it be just like double the
Or 0.
Yes. Yeah. Everyone get it? So that term equals to 0. Why? Because this guy is just this, right? There's no this part. So it's like something like this guy multiply this guy, right? This guy multiply this guy, right? So here 0, here 0. So the multiplication is 0. Does that make sense? That clear? Everyone? Right? Because this guy is just this guy, right? It's like this. And this guy is just this guy, like this. And then we multiply this signal by that signal, right? Clearly 0, right? Because nothing here and nothing here. Right? Yeah. So then this guy is 0. Okay, there we're good, right? So only this left. So basically we can comfortably write. So the power spectrum, the energy spectrum density is nothing but this guy. Right, this is our final answer, and we don't have this. Okay, so which is very nice, right? Because if you see, so this is the Fourier transform, right? The energy spectrum density is nothing but the square of this guy add the square of this guy. That's it. Right, it's very simple. Right? So any questions so far? Yes?
I'm a little bit confused in that part.
Which part?
Like after you did on the third step,
This guy?
Yeah, from that part.
Oh, how I get the third step?
Yeah.
Oh, just multiply them out, right? So this multiply that, this multiply that. We have two terms here, 2 terms here. Then we get 4 terms here.
Okay, but you have the conjugate.
Oh, conjugate is here.
Yeah.
So I take the conjugate inside.
Oh, okay.
Yeah, right. So this guy equals to just to take the conjugate here and take the conjugate here.
Oh, okay.
Right, and get this conjugate. Yeah, we have conjugate here as well, right? Because this is what we do, right? If something multiply the conjugate of itself equals to the absolute value square, or the norm. That clear?
What was the final answer for that?
Yes, this. So basically, maybe I can write here again to make it explicit. So the power spectrum density of S is nothing but 1/4 GF minus F naught absolute value square plus 1/4 GF add F naught absolute value square. Right, so that's the power spectrum. That's the energy spectrum density. Yeah, I keep calling it the power spectrum density because that is what we use in practice. Okay. Anyway, so yeah, that's what it is. Okay, are we good? Okay, great. Yeah, maybe we still have 10 minutes left. Maybe I can have time to cover one important concept. Yeah, the power spectrum density it's very similar to this, right? Everything works. The only difference here is that we define everything in terms of energy, but for the power spectrum density, we define everything as power, right, for periodic signal. So now we're going to introduce a concept that seems unrelated, right? But you're going to see the relationship in a minute. It's called autocorrelation function. Autocorrelation function. Okay, and then, so actually that has a very nice connection to power spectral density. Who heard of it? So who knows what the autocorrelation function is? Yeah, did you kind of see that in your probability class or random process class? No? Okay, no problem. Yeah, let me start from the beginning, right? So what does auto mean here? Right, auto basically means with itself, right? Auto means with itself, okay? We only have one function there, right, not two. And correlation, so this basically means that we're going to, or let's say autocorrelation, right? This autocorrelation means that we're going to correlate a function with itself, basically, right? But if we do an unchanged version of itself, it's kind of boring, right? So what we do is that we correlate a function with a delayed version of the function. Let's see whether it makes sense or not, right? So we're going to correlate a function with a time delayed version of itself. Okay, so that's what autocorrelation means intuitively. Okay, so now let's see what it means mathematically, right? So definition, autocorrelation function. Right, so now we focus on energy signal instead of power. Right, so for power signal, we can define something very similar, all right? So now again, let's see, we let G be an energy signal. Right, then is autocorrelation function is, it's called psi g, psi g tau. And you'll see why I use psi again here. Psi g tau instead of t. So that is nothing but the inner product between gt and gt minus tau. Okay? That's it, right? We can write it out. So that's nothing but we do an integral from negative infinity to plus infinity. We have gt. Yeah, don't forget, right? When we do inner product, so we need to write a conjugate here because g can be complex. Right, so that's the definition, right? So this is, and remember, so here t is the integral dummy variable, and eventually this function will be a function of tau. Okay, that's why we say this. Okay, that clear? Yeah, this is the definition. And again, now let's focus on the case where g is real. So that will make our life much easier. yeah, consider g of t, so that's real, right? And then let's see some property of the autocorrelation function, right? So now we can write that as this. So we don't need a conjugate, right? So the first property that we can see is as follows. So basically, yeah, let's do some substitution here, right? So what if we let t minus tau equals to u, right? Let t minus tau equals to u, and then we can see t equals to u plus tau, right? So let's use the u to substitute that and see what we get. Okay, then so t will become u plus tau times gu, and then we do the derivative of u. Sorry, we do the integral over u, right? And then compare this and that. So can you tell me what does that equals to in terms of psi g? Yes?
Is the psi g, it's of t or is it of tau? Or the second tau?
Oh, yeah. That's a typo. Tau. Very good. Yeah. Okay, so compare this and that. So this and that is the same. But here and here, so here is like u plus tau, here's t minus tau, right? So this is u minus tau, right? Therefore, so I can write that as this minus tau, right? So from here, we can see that phi g tau is even function, right? So phi tau equals to phi minus tau, right? So this is a very nice property of it. And now let's see. So if you see this kind of form, so it does look familiar. Gt times gt minus tau and dt, that familiar? So what's convolution? The same? Or no? Or a little bit different? Convolution is t tau minus t dt, right? Here's t minus tau, right? So, but because of this nice relationship, so we can still write this as a convolution. Let's see how we can do that. So basically what we do is as follows. We let g tilde t equals to g minus t, right? That's it. And then by using this relationship, because now g tilde t equals g minus t, then if we use g tilde t here, we just flip it, right? So basically, this equals to this. Gt. Now let's use g tilde t, tau minus t, dt. Okay? And because of that, now it's nothing but a convolution between g and g tilde, where g tilde equals to g minus t, right? Okay? So now let's see what is very interesting, okay? Because it's a convolution now between these two guys, okay? How about we do a Fourier transform of this guy, right? So we do a Fourier transform of phi g tau. Let's see what will happen, okay? So in the time domain, it's a convolution. So in the frequency domain, that will be a multiplication, right? So now we use gf multiply the Fourier transform of g tau, okay? So because g is real, then what is the Fourier transform of g tilde? G tilde equals to g minus t, right? So that equals to what? Yes, the complex conjugate, right? And then what does that equals to? It's a gf square, the norm of gf. What's that? Who still remember? It's our energy spectrum density, right? So now we have a very nice result, right? So basically, the autocorrelation function and the energy spectrum density, so that's a Fourier transform pair, okay? So if it is hard to compute in the frequency domain, we can do that in the time domain and vice versa, okay? So this is okay for deterministic signal, but this concept is extremely important for random signal. Okay, that we may talk about in the next lecture. Okay, I think that's it for today. So in the next lecture, we're gonna go through the power spectrum density real fast, and then we will talk about the modulation. Okay, thank you. Have a good weekend.